Hello, I'm going to show you today how to use the SANS 204 fenestration calculations as discussed in SANS 204 standards. This aligns with the SANS 10400XA standards that we've discussed in the lecture, and that's if you decide to follow the prescriptive route. It's important to note that the SANS 10400XA standards are going to be revised soon. It's probably going to be published very soon in a year's time. And they have a total different way of calculating the fenestration. So do in future see go to the new standards and basically see how it is done. But for the time being, the SANS 204 fenestration calculation method is still the way to understand the impact that your fenestration has on the performance of the building. I'm going to jump between different programs in order to show you how it's calculated. I hope you can keep up. You're welcome to contact me if you have any questions. So if we go to page 15, this was part of the lecture. I think you might remember that you basically need to calculate the total permissible conductance for your design or building, and also the permissible solar heat gain um, that that building can have. Now that's taking the net floor area and multiplying that with the conductance coefficient or constant and the solar heat gain constant. So you'll see that each climate zone has a specific constant, and one basically just calculates that. Now, if I can show you, here we've got a basic, just a very simple Revit model. Um, it's I think we can all see very clearly that it's possibly not going to comply at all. And if you go to the floor plans, you'll see that it's a simple 5 by 5 meter building. But if we are looking at the net floor area, we need to exclude the wall structure themselves. So a more complex building you'll actually have to deduct more floor area. But we end up with a 4.5 or 4560 times 4560 in order to get the total floor area. What this then would mean, you would then go and calculate that floor area. As you would have seen here, I know it's this is in region 2, so it's 1.4, and we know that it's 4.56 times 4.56, that gives us 20.8, the net floor area, and that gives us here a total permissible conductance, and I would have done the same in Excel, working out what the total solar heat gain coefficient is that's allowable. I think that is very straightforward, and that's possibly not very difficult to calculate. So it's just important to take your net floor area and multiply that with the constant that's being supplied. Now, the important aspect to now calculate is what the impact of the glazing is. So the first one we'll discuss would be the total conductance that that building is experiencing. So at the moment, and this is also deemed to change, we are basically just simply considering all the glazing within the building as a collective whole, and we're saying as a total, this gives us a total conductance. So you'll see the calculation, I think it's quite simple. It states here A1 times U1 plus A2 times U2. Now that refers to the area of window 1 times the U value of that window 1 plus the area of window 2 times the U value, and that can continue up to, I don't know how many windows you have. So you'll see in this model, we have 3 windows. So we'll end up saying A1 times AU1 plus A2 times U2 plus A3 times U3. So we need to understand that we need to calculate the area of 3 windows and consider their U value. Now in this model, I've basically used the basic single glazing U values as given by the SANS 204 document. I'm not going to go into double glazing and so forth. I think that's simple enough. But the most important thing to first do is to see what the size of the windows are. Now, you will know if you've designed it what the size is, but what we see here is 3 meters um, by, it's a 3 meter by, and I'll go to the section and you'll see it's a 3 by 2.5 meter window. So the north facing window and the west facing windows are both the same size, 2.5 by 3, and then the southern window is 1.5 times, I'll just have to confirm that, 1.5 times 2 meters if we just measure it. So it's just important you go and you use your model, you go and measure the area of each window. So if I then go to my Excel spreadsheet, this obviously becomes much more difficult when you have a really complex um, building, but I just basically named it north, west, and south. You can name it whatever. And I think if it gets to be a complex building, really be very rigorous in terms of your naming conventions. But the northern window effectively is a, a 3 times 2.5 meter window, so that gives us 7.5 square meters, and we know with the western window is the same, and then we know that the southern window is 1.5 by 2, so that gives us 3 meters. So you basically use the basic calculation, like we said here, area times the U value, and it's U value times the area, and that gives us a total value. Now you'll see here that this is the total value, we can say the total conductance for that window, and we need to add it all up to get a total for the whole building, and you'll see that it's permissible that I can have a total conductance of 29.12, and I see that if I add these 3 windows together, then I have 142. So it's obviously a lot more than what is permissible. This is then the point where you might want to start designing and changing things. You can go for double glazing, so I'll just thumb suck this very quickly and say, well, double glazing might be about 3.5. Now, double glazing does give us a reasonably better U value, insulative value. So let's see if we go for double glazing in all 3 cases, what happens? We end up with a total of 63. We still have a lot more than what is allowable. So you might actually have to start considering making windows smaller. And if you, for instance, choose to make them all 3 meters in total, you still struggle. So you might even decide to remove one in the end. So you might end up with 2 windows, or you might remove the western window and keep the north and southern window. Effectively, that's not, I think it's important to understand it as a design tool, and you'll have to adjust it in order to comply. But as you can see, it's a function of the area of the window and the U value, and that total basically starts defining whether it complies to what the SANS standards requires from you. Now that is conductance, total conductance. It's, I believe, possibly the easier one to deal with. The total solar heat gain coefficient is a little bit more difficult. It's not overly impossible to understand, but I think one needs to keep track of what you're working with, and there your naming convention of your windows are important. One thing to remember here, people often make this mistake. Remember that the U value looks at the insulative properties of the glazing. So something like double glazing makes a big difference there. Solar heat gain coefficient looks at the ability of the glazing to limit solar heat gain, which would mean the direct shortwave radiation entering the space. Now, double glazing has somewhat of an impact, but not that much, because it's still possibly clear glazing. So you'll have to start looking there at tints, or most effectively use actual solar control measures like a shading device and so forth. Remember, your shading devices must be permanent, So you cannot use something like a tree or the neighboring building. Unfortunately, I sometimes feel it's important to understand your context, but that is what the regulations at the moment state. So if you would like to calculate this total solar heat gain coefficient for a design, you need to calculate, in this case, the total area, and then you also calculate the for that specific element or window. You also need to include your solar heat gain coefficient, which again comes from your SANS 204 document where it's provided. And then you need to include the exposure of that glazing. So that really means whether it is west facing, north facing, or which direction it is, but then also whether it is shaded but with a shading device. In order to understand that, as you move a bit down the document, you will see there is under section, so it basically explains how you calculate it. Under shading, section 4.3.5, there will be an image which starts to define that or gives you indication of what they mean with it. It starts giving you certain dimensions that are important in order to understand the shading device. So one needs to understand both the size of the window, although it's not as critical in this case, but that's for the area, but you do need to understand what the height is of the bottom underside of the shading device from the bottom dimension of the window. Then you also need to understand what the extent of that shading device is. How far does it reach beyond the glazing? So you can consider how much shading it provides. And then really important, what they call G, is how much higher is that shading device above the top dimension of the glazing. And what they basically require or state there is, if you have a case where the shading device is more than 0.5 meters, so more than 500 millimeters above the glass, you need to halve the P value, which is the extent, how far it extends beyond the glass plane. You need to halve that, or it's divided by 2. So it limits the amount of shading it provides. What this means is you are going to calculate in the end the pH value, which is effectively the extent to which the shading is protruding beyond the plane over the height of the glazing up to the underside of the plane of the shading device. Should you have a case where the shading device is a fixed element that is covering the glass completely, something like a screen mesh on the western side, then you can simply assume that pH is 2. That's the highest value you can get. So that's important to understand. So if I go back to the Revit model, you will see that I now understand on the plans level, but if I go to the section, I therefore, if I look at this window, I understand that this is a 2.5 by 3 meter window, but the roof itself extends 600 mils beyond the glass, which this is actually incorrect, but let's assume it for now. But you actually want to measure it from the glass plane itself, so it's actually a bit more, but for calculation purposes, let's keep it for 600 mil at the moment. And then you can see that we've also measured it from the underside of that shading device to the top of the window, noting that it's less than 500, so we do not need to divide the 600 by 2. And then you see that the H value is therefore 2.5 plus 2,500 plus 325, which gives us 2,825. That's the H value. Now, this means every time when you think of a window, you will be considering how far and how high the shading device is above the glazing itself. So a typical example therefore is, and I will show you the first one. I'll go back to my Excel spreadsheet. So remember that you now calculated again the total permissible solar heat gain conductance for the building, and that's 0.12 times 20.8. That gives us a total. And you can say the northern window, we know that the area is 7.5. We've calculated that before. You've gone to your SANS 204 document, and you see that the basic solar heat gain coefficient is 0.181. So you can simply add it in there. And then I now need to calculate the E value. Remember, that's the exposure value. If I move up just to remind you where it's located, you can see here is the information for the glazing performance. But remember, we said here you need to calculate the E value. Now, the E value is then derived from the P over H measurements that you've now measured. Remember, we said that that's related to the extent of this shading device and how much higher it is above the glass. So in the annexure of the document, you'll find annexure C, which is a bunch of tables. And you'll see it's related to a specific climate zone. So you need to go to a climate zone. We're looking at climate zone 2. And in there, you see P over H, which means now you can use the P over H calculation that you've developed or calculated and see what the E value is, which is the exposure value. So if I use the northern window, for instance, we therefore see that it's 600, that's the P value, remember that, divided by 2825. Now, if I calculate that, let's just do it, 600 divided by 2825, that gives me 0.212. If I then go to my table, I can look for 0.212. It's between 0.20 and 0.25. So I know I can use the lowest figure, or you can use the highest figure as well if you wanted to, but let's use the lowest. I think that's more prudent. And you can now you just need to be sure that you use the right orientation. Remember, we're looking at the northern window. So we're not looking at any of the other west, south, and so forth. We're looking at north, and it gives us 0.51. If you then add 0.51 into your total there, you'll actually get your solar heat gain conductance coefficient for that glass itself. That then is how you continue. So if you take the western window, you simply go and measure the section through the western window. This is our western window. We do not have any overhang here. It's very small. You see here I've actually done it correctly. I've taken it from the plane of the glass. So it's again that's actually, and you'll take it up to the top of the window because it's not up there. So it's 2.157 divided by 2500. Now, if you calculate that, it gives you a total of I've calculated 0.06. And if you go to 0.06, you'll see it's up here at the top. And again, you simply go and read it from the table. So 0.06 would be close to 0.05. And now you're just simply going to use the west-facing window. So it's 1.19. That's the coefficient that you need to add in there. You add it into your calculation, and that gives you the total. Similarly, you go and calculate it for the southern window, and you end up adding it together, and you get to your total. And you can see here again, it's a very clear indication that our glass also fails in this case. So again, one needs to then change the size of it, or you might actually consider adding shading devices to it. Now, that's a bit more work because you'll have to go and test it, extend it, and go and measure the shading device and so forth. But one approach, for instance, is to say, well, I think I should not have the western window, for instance, and immediately you can see you've actually saved quite a bit, and it becomes a lot easier to achieve compliance in the end. So I've rushed through this a little bit. I do think the best way to learn how to use this is to, like all other standards, is to read through it. in the SANS 204 section, I don't think you need to read the whole SANS 204, but I would advise that you do go and read the relevant pieces related to the fenestration calculations, and then go and calculate it. You'll see it's actually a very simple process. It's just possibly a very tedious process. Now, many of you've worked in offices where you have a tool that's simple. You can just simply add it in there. The Excel spreadsheets has been developed already. Perfect. You can use it. I think that as long as you understand where it comes from, but it's I think any tool that makes it easier is a lot better. I think it's just if you don't have it, then basically just learn how to use it, and it's actually quite a simple process. You're welcome to contact me if you have any questions. I hope this helped a lot.